Welcome to this presentation about subsea wet gas flow lines. In wet gas fields, we often have three phases coming out of the ground: some water, some gas condensate, and typically a lot of gas. We will look at how it works, and we will do it by simulating the Ormen Lange, one of the flow lines there. This is a sketch of what that looks like. It's off the Norwegian coast. It's quite deep here, 850 meters. We have several wells here. They are about 120 kilometers from land, so there are long flow lines here with the multi-phase flow coming from the wells and going in towards Nyhamna. They are 30-inch flow lines, and there are also some other lines, some with control cables and some with mag, which is a chemical used to inject into the flow lines to avoid gas hydrates to form. That's kind of ice-like structures which can block the flow and create a lot of trouble. So as in most wet gas fields, we need to inject mag to avoid those problems. But we are going to do simulations of one of these lines, and we will do steady state simulations, and we will not inject any mag into the lines, even though we know that wouldn't have worked well in practice. It would have created gas hydrates, but we ignore that for now to focus on the main principles of interest here. Some of the interesting questions we will be investigating is what will the pressure in this flow line be, and is there a risk that we could get slugging? Is there a risk we could get hydrates? And the really most important question is, do we know how accurate the simulation results are? We have now started Flowline Pro again, just as we did when we simulated C-pipe. Setting up the Ormen Lange flow line here is exactly identical to how it was shown for C-pipe, so we won't do that again. The difference is in the calculation methods and in the results that come out of it, so we will focus on the results. The simulations have already been done. They're also slightly slower when you simulate multi-phase flow. So let's just pick some of the results and look at what we get. We can go for Ormen Lange, let's say 200 kilograms. Let's try this one, 200 kilograms per second here. And we can start by looking at the elevation profile for Ormen Lange. Here it is. The maximum depth is around close to 900 meters, and then it goes relatively steeply up from the deepest part, and it goes towards landfall, and it comes up here at landfall. We have also created this little icon which follows the pointer here, and it shows what the flow will look like at various places along the line in this case. So for instance, out here we have stratified flow. We can see the blue layer at the bottom of this little piece of the pipe, which is shown here, and we can see an oil layer on top of that, or condensate that really is, and then gas on top of it. So this little icon is scaled according to the actual data which have been calculated. And we also try to estimate how sure we can be that the regime, the simulator estimate, is actually correct. So in this case it says it's stratified flow, and we are pretty much 100% sure of that. That's probably a bit optimistic. Not very much is 100% sure in multi-phase flow, but that's what it claims in this case. And if we go to where it's a little bit steeper here, we see that it's a 74% chance it will be slug flow here, it says. And slug flow means that gas and liquid come in really steady state isn't really so relevant then, because that's a very transient phenomenon. But most of the way here, the simulation results tell us that we have stratified flow. And in the downhill sections, well, here we have a slight uphill section. In the downhill section, it's very, very likely we get stratified flow. We nearly always get that. The liquid is very willing to flow downhill, of course, while uphill, rivers don't like to flow uphill, so it needs a very strong wind to do that, or in our case, it is the gas flow on top of the liquid which drags it uphill. So here also we are likely to get slugs. I believe it is our job as creators of the software in use to estimate how likely it is that the results coming out of here is actually correct. This only tries to estimate whether the flow regime is correct, but that's in a way the beginning of the rest of the calculations involved here. We can also have a look at the elevations angles. So this really expresses the same as the plot we already looked at, but instead of the elevation itself, it is the elevation angle. So the steepest part here is maybe a bit less than 20 degrees. This is a 90-degree scale, so vertical would be 90 degrees. And then near landfall is also quite steep for a while. And that is where the slugs tended to arise for the particular mass flows we focus on in this case. We could also look at the flow regime directly here. There it is. And of course a flow regime isn't a number, so we have had to define a number to make this meaningful. So we have defined the number 0 as stratified flow and the number 2 as slug flow. And then we see that most of the way we do have stratified flow, and we have slug flow only a few places. If I click on this tab, I will see all the plots on one page, and we see it more clearly here perhaps. We can see that the slug flow happens exactly where it's very steep. That's where we are most likely to get slug flow in this case. Here and here it's steep, this was the angle, and that's where we have slugs also. What about the pressure? Well, it starts out with quite a high pressure here. We have presumed the inlet pressure to be 17 megapascal. And it was also presumed that the mass flow was 200 kilograms per second. And if that is true, then the simulations claim that it will lead to relatively fast pressure loss at the beginning. That's where it was steepest. So that already is an indication that much of the pressure loss here is due to the elevation change, not only friction. And here is a more gradual pressure loss until we reach the surface, where the pressure is around 12.5 megapascal in this case. The temperature goes down very fast at the beginning, and once it reaches what is the sea temperature, it is pretty steady after that. But that means the cooling happens relatively near the wells, and after that it wouldn't really help to thermo insulate these lines, because we wouldn't manage to keep it hot anyway. When we have multi-phase flow, it's best if it is hot, because that minimizes the risk of getting hydrates and other nasties in there. But that's not realistic to achieve probably with these lines by simply thermo insulating them. We would need to do other things like injecting mag, for instance. Let's go back to the pressure, by the way. Here's also the hydrate pressure plotted. and these simulations are done without any mag at all. We haven't injected anything to counter hydrate formation. And we know perfectly well that for wet gas pipelines we always get trouble with if we have water and we do not inject any chemicals to prevent hydrates. Hydrates is kind of ice-like structures which form when we have both gas and water. And the area here to the left of this line here, this line is the hydrate line. To the left of it we wouldn't get hydrates, but to the right of it we would. And the condition is worst here because the temperature is lower here. So for the temperatures we have, the pressure would have to be as low as this in order to avoid hydrates, and that's a very low pressure, so that's not practical at all. We need to do something with those to avoid hydrates. We can see from these plots. We can also look at the fractions. This is the gas fraction. That's how large part of the cross-sectional area in the line is full of gas. And for the most part it is even relatively close to 1 here. That's in downhill sections. And in the hottest end we have more gas because more of the liquid has evaporated there and is also dissolved into the gas. The oil, it increases gradually. That depends on how fast it flows. Some areas it flows very slowly, so it accumulates there. And water also accumulates in some areas, but not dramatically so. Well, water and oil, we can have the total liquid fraction here. If I click there, we see the total liquid fraction can come up into more than 20%, maybe 25% or something like that. So that's a considerable amount of liquid. We don't want it to go any higher because then we can get a high buildup and that can be problematic. There are also mass fractions. Well, we can plot those two perhaps. Here's the gas mass fraction, oil and water mass fractions. So even though the gas has a lower density than the other ones, it is for the most part more gas mass at any cross section than it is water or oil. The velocities, the gas goes at something like 3 or 4 meters per second through the line. The oil goes much slower, except for a very short area here which was downhill, where the oil flows much faster. And there's the water. So the water and oil is actually surprisingly, in this case the oil is surprisingly close to the gas velocity in some areas, while the water velocity is much slower. And that's because the water is lying under the oil, so the water is much better contact with the wall, we might say, and therefore it doesn't flow as fast as the oil does. The mass flows, here's the gas mass flow. We can also plot the total mass flow. Since this is a steady state simulation, the total mass flow is the same through the whole line. What goes into one end has to go through the whole line and come out again at the other end, and nothing changes over time in steady state simulation, so it has to be constant through the whole line. But we see the gas mass flow isn't constant, and that has to mean some of the gas becomes liquid. And if I plot the oil also, we see that's precisely what happens. We will have more and more oil or condensate, and that's because more and more of the gas condenses and become condensate as it becomes colder in the line here. And the water also, we get more and more water, but the water is quite little water. Let's plot that again, the water, since it is hard to read from this scale what the water mass flow is. Here we see it at the beginning. Water starts to come out of the gas. There was some water already when we started, but more and more water comes out of the gas and condenses as water. But then it stabilizes once the cooling has stopped, and even though the pressure continues to fall, there's practically no more water coming out of the gas. We can maybe plot the oil here at the same time. Yeah, here we see the oil at another scale than we saw at the previous tab. We get more and more condensate as we get closer to the outlet. We can look at the heat loss also. This is heat loss per meter of pipe. And the heat loss is large at the beginning because the fluid is very hot when it comes out of the ground and into the flow line. But once it has reached the same temperature as the seawater, it's practically constant. It varies only a little bit on its journey through the line. Here is a plot of how much gas becomes oil at different points along the line. It's kilograms of gas per second per cubic meter of pipe. So we have mass flow per volume of pipe here. And at certain parts it condenses much faster than in other areas. And obviously we would expect what the gas becoming oil to correspond somewhat with the gas becoming water also, because the water also comes out of the gas. And that's what we see here. This is water or gas becoming water, because some of what used to be gas now becomes liquid water. But it's very, very little liquid water coming out of the gas when we get further out into the line. Here is oil becoming gas, so that's boiling. We do have a little bit of boiling, but not much. So there are some points on the line where we actually have boiling also, says the simulations. And water becoming gas, that means water boiling or condensing, or evaporating into the gas, practically zero. We can plot the densities also. The gas density, it varies a lot. It increases a lot as it becomes cooled down, and then it expands a little bit again. It becomes lower as it expands towards the outlet where the pressure is lower. The oil density also changes a bit, and the water density does that. Interestingly, we see that the water density actually increases at the temperature is reduced, while the oil density actually is going down as the temperature goes down. And that's because the composition of the oil also changes. The type of gas becoming oil changes. So it's only heavier components which already have become liquid at these high temperatures. So it's lighter and lighter components coming into the condensate. That's why it actually reduces its average density as the temperature false. I'll generate a report now then. Takes a bit more time with this larger report. It comes. It's for the most part the same results we have already seen, but some additional results here as well. Total length 121.7 kilometers. The various pressures, the inlet and outlet, and the position of and the maximum minimum pressure and the position of them, and so on for temperatures and fractions and so on. Maybe interesting to see what the largest gas fraction is. It is actually the maximum is 0.999. That was suspiciously high, I would say. Maybe that's just at the inlet before it starts boiling. Oil fraction comes up to 11.8% and the water fraction comes up to around 17%. The flow regime is stratified 97.45% of the time, and the likeliness of this being true is very high most of the time when it is stratified. So we can be reasonably sure here, says this simulation. Slugging also has a very high likeliness when it occurs. That's simply because it happens where we have uphill, and the uphill is very well defined in this case. Now these numbers can be totally different especially if we have lower gas flows, because then liquid accumulates on many more places. Accumulated liquid volumes can be quite important. The line is 93% gas filled in this case. Nearly 3% is oil and nearly 4% is water. The oil takes about half a day to go through the pipeline, while the water takes terribly long time. It means the water for the most part almost doesn't move at all. The fluid composition, and it has detected hydrate danger, obviously, as we knew it would when we didn't have any mag in the fluid at these simulations. And here we can see the composition of the fluid. It's about 0.5% of water, the mass fraction. And then there are various light components, especially methane, since this is mostly a gas field, but with some heavier component, and that's why we get some condensates here. Some of the other fluid properties involved: surface tension, viscosity, Prandtl number, and then come the plots. We have now restarted the program, and we wonder what happens if we increase the mass flow even more. So we'll load the file here where we have 380 kilograms per second mass flow, which is quite much higher. Now, one problem with the simulations we have seen is that we do not really know how accurate they are, because we do not have any measurements available. So we have to do the next best thing when we want to verify this, and the next best thing is to compare against another simulation program. And we have here chosen to compare against Olga, so we will load some files simulated with Olga also and see how it compares with that. So we add more files here and we go to some Olga files we have available, and they are simply text files because they are copied and pasted out of Olga, and we have done the same data there. We use the same PVT files, and here's exactly the same case set up in Olga also. And Olga has actually two different ways of calculating steady state flow. They also have something they call HD, and we have done simulation with that as well. So let's load that too. So we have one more Olga result here, 380 kilograms per second, and this is the HD file. And we can click here to get all of these things plotted automatically. Let's do it the lazy way. So now he plots for several files at the same time. Let's go back to the first plot again. Here are the pressures, and they are not very different actually for the Olga results and the ones coming out of Flowline Pro. We have the green line here is Flowline Pro result, and then we have the hydrate line, which we have discussed before, and here is the pressure coming out of Olga and Olga's first method, and here is the pressure as it comes out of Olga HD. So in this particular case, Olga's two methods actually deviate more from each other than Flowline Pro deviates from one of the Olga methods actually. And the temperatures also agree really well with each other. Here are the mass flows, the total mass flows, which are actually supposed to be totally constant. They are very constant in Flowline Pro. They aren't actually completely constant in Olga, but they are reasonably constant though. They vary with it seems to be less than 1%. So this we have to say is straight lines for both simulators. Here is the gas mass flow. They also agree really well with each other. That means they end up claiming the boiling and condensation to be very similar in both methods. And here is the oil mass flows, also agrees really well. The water flow, the blue line here is what comes out of Flowline Pro, and these are the two Olga methods. Actually, Olga has a bit of noise on the curves here. It goes up and down even though the pressure and the temperature does not go up and down. So this is a little bit of numerical noise coming out of Olga. But roughly speaking, we can say the results are very similar. And here is this is the gas fraction, and yeah, this was the mass fractions we looked at, while these are the volumetric fractions, and they are also surprisingly similar. But we have to remember this is with a high flow, and then it is easier to get similar results. And oil and also water, the water deviates a bit more from each other. So the blue line is what comes out of Flowline Pro, but we still have extremely small water fractions in this case. It is about 0.5% according to Flowline Pro, and Olga claims it is somewhat less. But that is next to nothing anyway. So for this high total flows, the gas blows out all the liquid really fast. That's what all methods tell us in this case. And here's the gas velocities. They are also very similar. They are actually very similar between Flowline Pro and one of the Olga methods. The HD method leads to a little bit higher gas velocity. But this is way better agreement than you would expect actually from the inaccuracies involved. So this is a little bit of luck also, we have to assume. And also the fact that we are dealing with the simplest case, namely very high velocities. And oil and water also agree pretty well. Again, the water velocities disagree somewhat more, but they are reasonably high here, much higher than they were in the previous simulations. They are up to 4 meters per second for Olga, and while Flowline Pro say some below 2 meters per second. The flow regimes are purely stratified, says Flowline Pro, and says one of the Olga methods, while the other Olga method says we have very brief moments of what actually one means annular flow. So we have annular flow for very short moments, but we do not have slug flow at all, and that explains why the agreement is quite good. So we can plot this also in the report, just at least so that we have the report. And we see 100% stratified according to Flowline Pro. And otherwise, and the transfer time is much lower now, about 5 hours for the gas from it enters the line till it comes out again, 7.5 for the oil, and about 14 hours for the water. So actually better agreement than we would expect from the inaccuracies we know are involved in these calculations. That the good agreement does not prove that any of them are correct, of course. It's simply two simulation programs we compare with each other here. The next example will be with this 100 kilograms per second. So that's a lower mass flow. And then we know the tendency of slugging tends to become higher. Let's go back to Flowline Pro and files. 170 bar in that case was the inlet pressure. Let's try that one. And again we add some Olga simulations also. These Olga simulations were done a while ago with Olga 7, Olga 7.1 I believe it was. So Olga has come up with later versions now. They may have changed how they do these things. And Olga HD, which I also compare with here, I believe at the time was considered an experimental version of Olga. So let me also add Olga HD for this 100 kilograms per second. There is the HD, okay. And let's have a lot of plots for these also. Now we have more slugging here, obviously. Going back to the pressure, now we see more differences here. But it turns out Olga HD leads to a much lower pressure loss than does Flowline Pro and the traditional Olga. So that's quite a significant difference. the experimental version of Olga, we might call it, in Olga version 7, disagrees more with itself in a way than does Flowline Pro. And their temperatures, they are easier to make agree well with each other, and they agree really well here also. Again, total mass flow. There are some very minor bugs in Olga there. The mass flow makes jumps even though it's supposed to be constant. But that's probably some numerical noise only. The gas mass flow also is quite different in the Olga HD version, because when the pressure is different, we get more gas because the pressure was lower there, we remember, and then we get less condensation. And the oil mass flow they agree very well, except for Olga HD. And it becomes a bit more complicated with the gas fractions. We can, in all the chaos here, we can see that they are somewhat different. Maybe I should take away some of them so we can see better here. If I take away, let's see, the HD at least, and then we still see some differences here in how large the gas fractions are between Flowline Pro and Olga. But overall it's similar enough that we get very similar pressure losses. And the same can be said about water and oil. So we see there are considerable differences, especially in Olga HD. It's quite different from the others. And then slugging, it's a bit hard to tell from this, but maybe again we remove some of the plots. No, I shouldn't have removed that one. Let me remove HD. And then it's relatively similar, actually, the flow regimes between Flowline Pro and Olga. Last results, very, very low mass flow, only 10 kilograms per second. That is so low that we wouldn't really produce that way, but it can be relevant in order to see what happens in situations where we get down to very low flow. That can happen during startup, it can happen for unintended reasons. And I think we skip Olga HD this time. We just go to Olga. Here is the 10 kilogram per second. And let's again do the plots. Much more slugging now. But again, the pressure losses are extremely similar for the two methods, for Flowline Pro and Olga. And of course we have a much larger region where hydrates will be a problem now, because when it moves so slowly, we have a very, very slow flow here now. Then it cools down much faster, so the temperature drops down to dangerous level at a much earlier stage. Other things. Mass flows are also extremely similar, and the gas fractions, they deviate here and there, but not enough to make a huge difference. We do have one significant difference here though. The oil fraction or the condensate fraction, if you like, is quite much higher in Flowline Pro than it is in Olga. On the other hand, the water fractions are opposite. The water fractions are lower in Flowline Pro than in Olga. So altogether, the overall liquid fraction is actually quite similar in the two programs. The velocities are also pretty similar. We see here the oil velocity is a bit higher according to the Olga results, but not enough to make a huge difference in the overall result. Now maybe we should switch off the Olga flow regime just to be more easily see what is what here. So this is the flow regime now coming out of Flowline Pro. So we see that we have slugging in maybe half of the line, and then we have stratified flow in the rest. And that isn't very different in Olga. If I plot the regime in Olga again, while Olga is varying a bit more, I can switch off. We see the Olga flow regime jumps a bit more from stratified flow to slug flow, but on average they seem to be very similar actually. The simulations have shown us that we are dealing with many types of uncertainties when we simulate three-phase flow. It is much more complicated and much more uncertain than simulating single-phase flow. We have seen, for instance, that getting the flow regime right can be difficult in some cases. And we have seen that we can have liquid accumulating in the wet gas flow line. That can create trouble and a lot of slugging. We have difficulty determining slug lengths and slug frequencies. There are models for doing all of this, but we don't know exactly how accurate they are. The fluid properties is also a challenge. We need to know such things as density and many other things as a function of pressure and temperature, let's say. But since we have many wells connected to the same flow line and this changes over time, we will generally not know the properties very accurately. And especially whether or not we form emulsions, not something we discussed much during the simulations, but that is a problem. It determines what the friction ends up being and what the viscosity of oil and water ends up being. Friction in general is always difficult, and it's much more difficult in multi-phase flow than in single-phase flow. If we inject mag, which we did not focus on, but which needs to be focused on when we want to study all sides of the problems here, one of the difficulty then is to know how the mag is distributed. It needs to be in the water to do any good. If it accumulates in the oil or are on the wrong places, not where hydrates tend to form, then we have a problem. So there are uncertainties in that as well. Elevation processes are extremely sensitive to the flow line's elevation angle. So when you are close to horizontal, if it's a very, very slightly uphill, you get much more liquid accumulating than if it's very slightly downhill elevation. A tenth of a degree can make a huge difference. Mostly so if you have low velocities in there. So that makes it hard to know the elevation profile accurately enough for that to be to produce good results in the simulations. Also, all sorts of unusual events create problems. If you have you have unintended shutdown. When you start up for the first time, you may have liquid accumulated and so on. These are things which are difficult to know accurately. And flow measurements is in general also difficult. There are flow measurement devices on Ormen Lange, both purely software-based ones, which kind of calculates from the simulations and from some of the simplest measurements we have. And there are also hardware, real units standing there trying to measure the multi-phase flow from each well. And the overall simulation model has quite severe uncertainties in it because of all this. So the main conclusion has to be precisely that. Mechanistic models for multi-phase flow are still quite uncertain. And we need quite large margins when we design such systems. We need to have more mag available, let's say, than we thought would be necessary. We may need to have more pressure available. We may need to have subsea compression, even if we thought we could do without. We may need it for some cases where we otherwise may accumulate so much liquid that the whole production stops. Or we may, as in Ormen Lange, need to have two flow lines so that we can, if too much liquid accumulates, we can blow it out by blowing gas through one and back in through the other one. So we need to have certain types of redundancies to be on the safe side. I also think that quantifying the uncertainties in the simulation software itself is very desirable. So the software should come up with numbers giving us some idea about what the uncertainties are in the calculations we have done. Most of the software out there today doesn't do that, but it would be very desirable if it did. There's more information about multi-phase flow at this internet site. You can also download free copies of some of the reports we have created during this video. And there are 2 books describing not all of the theory used in the simulation program we have used here, but quite much of it, and it gives a good background in how to use such simulation programs. Thank you for listening. I hope you have found something of interest here.